Hello and welcome to another video. Today I'm going to talk about some of the more recent organic hydroponic experiments I've been doing. And to start with, I would like to show you kind of where things begin. This is my homemade biofilter. It is a mix of things I have. I have some clay pebbles, leca, as it's called, light expanded clay aggregate. I have some gravel. And I have some old MBBR carriers. These are not made to be put like that. They're made to be moved in a reactor, but this is what I had to create surface area. And then I have a pump, a small water pump that pumps from the bottom to the top, and in the top it gets some of the air, and that's how I am creating a nitrifying process. So to recap, this is mostly where I'm doing the anthroponics, and if you haven't seen the videos or you don't really know, just a small recap. We start, of course, with the urine, which we convert to ammonia through the volatilization of urea to ammonia. This, in this case, is done either by storing the urine or by adding some watermelon seeds crushed and dehusked, which have the urease enzyme which speeds up the process significantly. But that's the first step before it reaches this biofilter. Here, what happens is with that ammonia eventually becomes nitrite and then nitrate through the addition of air and by promoting the growth of nitrifying bacteria in the high surface area environment. However, that's not all that I'm adding here. I'm testing something which you could call bioanthroponics, I guess, which is mixing bioponics using food wastes to create liquid fertilizer, and anthroponics, which is using human waste to create hydroponic fertilizer. So on top of the urine, I'm also adding vermicompost leachate, bokashi leachate, and some wood ash. And why am I doing that? I'm going to explain to you in just a second. So initially, once we started doing some testings with anthroponics, just using urine as a nutrient source, we noticed it wasn't really enough to grow, for example, more nutrient-demanding crops like cucumbers to the way we wanted. We were observing discoloration of the leaves, some clear nutrient deficiency signs. So urine by itself is not enough, which made us think that we need to come up with some sort of recipe so we can make sure the shortcomings of urine can be complemented to grow any type of crop. And one of the things we've experimented in time was to, for example, first to combine the vermicompost leachates with the urine, and also we tested urine and wood ash. I have some technical reports about that written, but more recently what I tried to think was, how can we balance the things that we want so that we can achieve the optimum growth? So first we start by observing that the processed urine that we add in anthroponics has a high pH, and it's mainly a source of nitrogen. For the vermicompost leachate, from the tests I have done and the literature I've seen, we can see also that tends to have a high pH, so it's basic, also a source of nitrogen, already in the form of nitrate, but also has all these other things like potassium, magnesium, a bit of iron even, phosphate, sulfate. Then on the other hand, things like bokashi leachate, which is something I'm experimenting with recently, has a more acidic pH, and while also being a source of nitrogen, but more in the terms of ammonia, it can also supplement iron, potassium, phosphorus, calcium, magnesium. And finally, wood ash also has a high pH and mostly supplements potassium and magnesium. Now, however, you will observe here that a lot of these are increasing the pH of the whole mixture. So depending on the amounts you add, you might end up with high pH, or maybe you might end up with low pH if you add a lot of this. Also because this recipe is going into, for example, the biofilter I just showed you. So that already, the process of nitrification reduces the pH significantly sometimes. So to have a bit more control, because the pH is very important in how the plant is able to uptake all of these nutrients, we have some sort of controls to put the pH up or down depending on what we need. So one of them is phosphoric acid. It's very typically used in hydroponic systems and has a little bit of phosphorus, and it's generally a safer acid to handle. That will lower the pH. And on the other hand, we have something like lime that is also easily sourced and available, and that can help us increase the pH if we need to. So this is the working hypothesis that I was starting from. So I've been adding to that biofilter some urine that has been processed or is processed in the biofilter, some vermicompost leachate, some bokashi leachate, and some wood ash. The amounts, of course, have been somewhat random. I think I've generally kept to 500 milliliters or just about of urine, and then about 200 milliliters of vermicompost leachate and bokashi leachate, and wood ash just a few spoonfuls. Sometimes I don't even add that much because I'm a bit concerned about maybe some of the heavy metals it could be, because I was not making this myself, whereas these ones I have made myself. And then because I know most of these are increasing the pH, I have measured that, so I also added a little bit of phosphoric acid that I have. And after waiting some weeks to really make sure I had a nitrifying bacteria culture grown, and that everything had time to mix properly and be somewhat processed by that bacteria, I then use it to grow some plants. So which plants did I grow? I will show you just now. So these are the things I have been growing using this recipe, and I tried two different systems. I'm just growing basil, and these were started, curiously enough, at the same time that I started these mineral hydroponic basil, which have not grown as much as I would like, although as you have seen from other videos, I can grow them quite as large as this one in other systems. So I think this is more of a limitation of the wine bottles that I'm using, and especially the lack of light. But anyway, so what do we have here? Here we have just a normal bucket. In this bucket, I have added a mixture of 50% cocoa and 50% perlite. Mix it well, and then I added a little feeding tube, so when I add the nutrient solution, it goes all the way to the bottom, and then I sub-irrigate. And yeah, you can see that the basil has been growing very, very well. There's no signs of deficiencies. It is possible just urine would have achieved the same effect, as I have also done so previously. But I think the more interesting part here is that after the whole the energy I've used in the biofilter, I am not using energy other than the light to mix the solution or to aerate the solution. I'm just sub-irrigating and letting it grow passively once I got the nutrient solution made. So this is in effect passive bioanthroponics. It's low energy after the nutrient solution has been made, and even then I have not used a lot of energy. And of course, this is my favorite large leaf basil. So that's why it's not just a normal basil that has grown a lot. It's a special variety that does produce bigger leaves. The leaves that can grow as big as my hand. There are just a little bit of discoloration here, but that I think is because it's older growth. So yeah, this is a very successful experiment, I think, and I add the nutrient solution maybe once a week or even sometimes less than that, and and yeah, it's been I think it's been a success. And I also, however, though, the growing medium was pricey a little bit, and I'm not sure this would work as well if it was just water, for example, like a deep water culture system or a Kratky system. So to save a little bit of that cost, I took inspiration from Mr. Kratky himself and his YouTube channel, and I created a pot in tray system. So in this bigger outer pot, I have put a smaller pot inverted and then filled the surrounding volume with the 50% mix of cocoa and perlite. So I use much less cocoa and perlite, and there is a big gap of air, or should I better say moist airspace, which is important for the Kratky method or the passive method. And the water is delivered through this tray. It's not optimal because there can be algae growth, there can be mosquitoes growing, but it's just to test the system. The idea is that you add your nutrient solution here, our recipe, and this pot has holes, and through the wicking effect, the water moves slowly up towards the roots, while also the roots having enough access to air, so there's less chances of things like root rot, which is a big concern usually, especially in organic hydroponics like we are doing. And of course the roots, they will explore where they can explore. So you can see here that they have found direct access to the tray. So they were not constrained to the space here. But regardless, there has been significant growth. I mean, almost as good as this one. So I would still call this a very good success, and more importantly, a success that used even less material. So this is where I'm at right now. I am doing. I think we have reached here a very interesting step, which is that we have, I have proven before in a previous video that you can use, for example, vermicompost, dried and crushed, and add that as a fine powder and grow passively. That still used energy, for example, for the grinding and the drying. Here, we used a little bit of energy to take that food waste and human waste and convert it into a useful, very useful, I should say, even hydroponic fertilizer, and it works. So I think the next step, after having shown this to work, will be to test some maybe more demanding crops, maybe to try something like a smaller tomato plant that I like to grow as well. But as you can see, these are growing well. So before I do my next experiments, I will make pesto out of these. So as we continue our journey to try to make a more sustainable hydroponics that still has a benefit in terms of high yield, fast growth production, we continue to tackle the different aspects. So we try to think more deeply about the energy aspects and the material aspects. So as you've seen, we are using material. Cocoa, for example, is fairly sustainable. Perlite as well, and they can be reused, which is great. They can be also sterilized if need be because of a pest infection. So really the thing that we are dealing with now would be the nitrification aspect. How can we use less energy for that? I'm already using what I think is the least amount of energy, instead of even running an air pump that has a certain diffusion rate of the oxygen in the water. I'm trying to use a water pump that's moving the water slightly and having more of a natural aeration, let's say. But it is possible that we know plants can uptake uptake ammonia directly rather than nitrate. So it is possible to maybe skip part of this process. So just storing the urine, waiting for the volatilization to happen from urea to ammonia, and then adding the ammonia, already mixing with all of this. This is something that I will investigate later on. As far as these two are concerned, these are fairly low energy, fairly passive methods. The only energy used here is by the worms or by the bacteria. And concerning the bokashi, as you've seen maybe in one of my other videos, where typically people rely on buying a bran, I know you can also make your own fairly quickly from a previous culture that you have made from a bokashi. So there is some element of reusability. Of course, if you use it a lot, maybe you dilute the cultures, and then they might not be as effective, but that is possible. And the wood ash, if you have access, of course, to wood, and you burn it for whatever use, you can also achieve that as a source. These are that's the more complicated aspect. So that's also why I wanted to map out how each are affecting the pH, because it's possible that, for example, in a low energy future, you might not be able to harvest or produce these so easily. So you might have to rely on using more of using these might be enough, and you use these to supplement the pH, for example. So these are things that I'm still thinking about, and I'm glad to have any input if you have it. But yeah, these are still some of the kinks to iron out so that we can achieve a very complete and low energy nutrient solution for sustainable hydroponic growth.